Hi, today we're going to continue talking about span. So before we were talking about span in regards to can we build is a vector in the span of a set of vectors. So we were basically asking, hey, can we build a particular vector from a vector space using these building blocks and basically doing vector space properties, which are addition and scalar multiplication. So now we're going to kind of extend this idea, and you should have already done the magic carpet and hoverboard ice sheet. If you haven't, pause it now, work on the previous 2 pages where even Archer are trying to travel around. Now we're going to talk about, hey, what if we wanted to span a whole vector space, so not just one particular vector. What if we want to build everything from a big space? So we have a definition. We say that a set of vectors, v1, v2, v3, spans a set x, if x is equal to the span of these vectors. If this is the case, then we'll call these little vectors v1 through vn a spanning set of x. So the first question I have is true or false? Are spanning sets unique? If I have vectors that build a full vector space, you think they are unique. So pause this for a moment. Think about it. Okay. So you may recall, here's a hint, you may want to look back at example, I think it's 411, when we were looking at the span of x and 1. Okay, and we actually said that this could build the space P1, but we said this was also equal to the span, sorry, my pen's acting weird, of x and 2. So then we can say, hey, this is great. We can build P2 or P1 from x and 2 building blocks or x and 1. So the answer is that spanning sets are not unique, so this is false. Okay, so one of our questions is how can we show that a subset of vectors spans a vector space? So what this basically means is that we want to produce any vector W and big W using a linear combination of the vectors from our set. What's the problem though? When we're talking about vector spaces, how many vectors are usually in most vector spaces? Infinitely many. So one option could be we will take every vector individually from our vector space and we'll see if we can build it one by one. But then we'd be here till forever. So the question is, how can we actually check them all? How can we actually do this? And the key here is to pick an arbitrary representative. So pick arbitrary representative. See, my handwriting is still pretty bad with this pen, so hopefully you can bear with me. So if I can show that I can build an arbitrary representative of a vector, of a typical vector in the vector space, and I can build it, then I should be able to build any particular vector in that vector space. So the idea is that you pick an arbitrary vector u and see if you can build it. So let's think about it. What is an arbitrary vector representative for R3? Well, we need 3 spaces. We could do x, y, and z. We don't know what x, y, and z could be. We could also, again, these are just variables. We could pick a, b, terrible b, and c. Would 3, 0, 1 be an arbitrary representative for R3? No, because we have particular values for each of these. This is a particular vector. It's not an arbitrary representative. What would be an arbitrary vector representative for P3? Remember, this is the polynomial space of cubics. Well, here we can determine different cubics by the coefficients in front of their x's. So an arbitrary representative for P3 could be ax cubed plus bx squared plus cx plus d. And this is why I often have, when you're building things, using the alphas and the Greek letters, because a lot of times people use A, B, C, and D when they're setting up their arbitrary representatives of vectors in R3 and in P3. Okay, so note that spanning sets need to be a subset of the space they're actually going to try to build. So for example, if I look at D, the set of x1 and x squared, it can't be a spanning set for P1. Why is that? That's because D is contained in, or sorry, is a subset, okay, of P2. In other words, we have quadratics. Here we need to have linear cases, so which is not P1. So we don't even consider it for our spanning set because it's not in the right space. It lives in P2. On the other hand, D could be considered a possible spanning set for like P2 or P3 or P4 because P3 and P4 do contain the x squared. But P1, the highest x value that it contains is just an x. Now, some people might be saying, well, what if I let the A and the B be x's? Or x squares. Remember, a and b's are just scalars, they're not the x's. Okay, so they're not the polynomial part. So let's do a couple of examples. Let's continue to explore P1. Okay, so it's the set of all linear polynomials. And let's determine whether or not the following sets are spanning sets for this P1. So let's look at A. I want to determine whether or not this set can span P1. In other words, I want to know, can I build any element from P1 from these two vectors? And what I can do is I can pick an arbitrary representative for P1. Rep. And an arbitrary representative can be ax plus b. And then I try to build this using my two building blocks. So what do? I make a linear combination of 200 and 1. So I have alpha times 200 plus beta, that's a terrible plus beta times 1. And I ask myself, can I build any ax plus b? Well, it turns out that 1 and 200 are like terms, so this is actually just something that is a constant. Would we ever be able to build the x part? No. So the problem here is that we can't build the x part. So for example, we can't build x plus 2, okay, from this. Okay. All right. Now, how about B? Sorry, we're running out of space here. For B, again, we pick an arbitrary representative for our vector in P1, and we take a linear combination. In this case, there's only one value, so I just have alpha x. And the question is, can I build anything where A and B can be anything from just alpha x? And the answer is no, because we can't ever get just a constant. So we can't build x plus 1. In this case, if I tried to solve this with the alpha x, we would get alpha is equal to 1, but then there'd be no way for us to actually get the other one. Okay, actually, we could even make this be a little bit more. If we had like 9x plus 1, then alpha would equal 9, but we still wouldn't know what to do with the 1. Okay, so neither of these, neither A nor B, are spanning sets. Alright, what about C? Now, you may have noticed from A and B that we had a set where we just had constants and then a set where we just have x's. Since P1 has x's and constants, we need to make sure that when we have a spanning set, they have those things. So C is a little bit better because we have two elements and they have x's and constants. So let's see if we can build. So again, we start with an arbitrary representative, ax plus b, and I want to see if I can build it from alpha x plus beta times the quantity x plus 1. Now, what I need to do next is combine like terms on the right side. So I'd get, notice that alpha x, and I can distribute the beta through. So we'd have alpha x plus beta x plus beta. And I can combine alpha x plus beta x. Just like if you had 2x plus 3x, you'd get 5x. Here we have alpha plus beta times x plus beta. And so now we want to solve for A and B. We want to see, can we find alpha and betas such that we can find A. So what do we need? We need alpha plus beta to equal A, and we need beta to equal B. Now our goal here, this isn't enough to tell us if it's spanning. We need to actually be able to tell alpha is, we need to solve for alpha so that it's only in terms of A and B. Because if you think about it, think of it as a game. Someone's giving you an arbitrary ax plus b, and you want to be able to tell from A, like be able to tell them what alpha and beta should be given just A and B. So this one is pretty easy. So we have beta is equal to b. This is good. That's in the right form. But the problem here is that we need to solve this one for alpha. So if I solve for it, alpha is equal to a minus beta. This isn't good yet, okay, because alpha is dependent on beta. We don't want it to depend on the other Greek letters or the other like building block scalars. We want it to be only in terms of A and B. But what do we know about beta? Beta is equal to B. So that means alpha is equal to A minus B. This is good now because we have alpha only in terms of A and B, and we have beta only in terms of B. Because I was able to find alpha and beta only in terms of A and B, then yes, we can build anything. So for example, if you wanted to solve for 3x plus 1, beta would be 1 and alpha would be 2. Because we'd have it, A is equal to 3 minus 1. Okay. All right, let's do the next one. Let's do D. All right, so again we have 2, so we want to come up and solve this, and we have ax plus b, an arbitrary representative of P1. It's equal to alpha times x plus 1 plus beta times 2x plus 2. All right, so the first thing, that plus is terrible. So the first thing we want to do is distribute the alpha and the betas. So we get alpha x plus alpha plus 2 beta x plus 2 beta. Right? I want to combine like terms, so in front of the x I get alpha plus 2 beta times x plus alpha plus 2 beta for my constant. Alright, so now I set up my system. I have A should equal alpha plus 2 beta, and B is equal to alpha plus 2 beta. Now you may notice this is a problem, okay, because what do we notice? A and B will be the same no matter what. So the question is, how can we actually show that this is going to be a problem? Again, our goal is to solve for A and B, or alpha and beta, in terms of A and B. So what we need to do, one way to kind of think about this, and we could have done this for C as well, is to try to solve for this. Okay, some of you may notice that no matter what happens, if I try to build using these building blocks, I'll only get things where A and B are the same value. But if I was trying to solve this, remember, if I'm trying to solve for alpha and beta, those are our variables, so I have 1 and 2 for the augmented matrix, and then A, and then 1 and 2 for B. Row reducing this, I can eliminate the 1 in the second row by taking row 1 minus row 2, so I'll get 1, 2, A. If I take row 1 minus row 2, I get 0, 0, A minus B. So the problem here, if we notice it, if I'm trying to solve this, this only has a solution when A minus B is equal to 0. But what do we know about A and B? They can be anything. Okay? But A and B can be anything. So the problem here is that this has no solution in general, so it's not a spanning set. Okay. All right. What about E? Okay. Well, let's try to build AX plus B from here. I'll siphon off this. In fact, I can use a different color for this guy. Ooh, maybe I'll use green. That will be fun. Alpha times x plus beta times 1 plus gamma times 3x plus 4. Alright, so same thing, we want to distribute and combine like terms. So we get alpha x plus beta plus 3 gamma x plus 4 gamma. Combine like terms. Notice that we have two x terms, so the constant in front of it would be alpha plus 3 gamma times x plus beta plus 4 gamma. Again, we want to match these up with the ax plus b. So we have A is equal to alpha plus 3 gamma, and B is equal to beta plus 4 gamma. Now, we can set up the augmented matrix. So here we have three variables actually. We have alpha, beta, gamma. So for the first one we have 1 for the alpha. We have no beta, so we have a 0, and we have 3 in front of the gamma, and we want that to equal A. For the second one we have 0, we have 1, and we have 4, and B. Now, my question is this in row reduced echelon form? Yes, it is. So when you look at the 3 and the 4, this row is telling me that which variable is free. Gamma is free. So gamma can be anything I want. So again, our goal is to solve for alpha, beta, and gamma so that we can tell, okay, what do I need to pick for all of these? Well, here I can pick anything for gamma. So I'm going to pick gamma equal to 0 because that's easy, but I could also pick gamma equal to 1. Then I have to solve for alpha and beta in terms of gamma. But if gamma is equal to 0, then alpha just needs to equal A. So in other words, if you go back to the beginning, this first line, if gamma is equal to 0, well, what does alpha need to be? It needs to be A. What does beta need to be? It needs to be B. You can also do that by solving for alpha. So alpha is equal to A minus 3 gamma, beta is equal to B minus 4 gamma, and gamma is just equal to gamma. So if I pick gamma equal to 0, then I can have a nice algorithm for alpha and beta. But this isn't unique. How many solutions does the system have? Infinitely many, because I can pick whatever I want for gamma. But I'm lazy, so I'm going to just pick 0, which means then alpha is just equal to A, and beta is equal to B. So have I been able to solve alpha, beta, gamma only in terms of A and B? Yes. So it is a spanning set. Spanning. Hooray. Okay? All right. Okay. So let's show that R2 is spanned by both of these vectors sets. So again, what are we wanting to show? We want to show that R2 is equal to the span of these two vectors. I'm going to go ahead and label this. Oops. Hold on a second. V1 and V2. And this is U1, U2, U2, and U3. So we want to show this is equal to the span of V1, V2, which is also equal to the span of U1, U2, U3. Okay. All right. So, how many vectors are in R2? Infinitely many. Do we want to show all of them? No. So we need to pick an arbitrary vector in R2. And the arbitrary vector we're going to pick, it could be A, B. I'm going to do X, Y just to show you a different way. So we need arbitrary. You could also have picked A, B is also good, or UV is okay. And so what we want to do is we want to see, can I build this arbitrary representative from R2 using V1 and V2. So I want to find constants, alpha and beta, such that when I take alpha times V1 plus beta times V2, I'll get values for alpha and beta only in terms of x. So in this case, let's go ahead and try to simplify this. Okay. So we can look at the first row. This can give us the equation x is equal to alpha times 1 plus beta times 0. So plus 0. And y is equal to 0 plus beta times 1. So can I solve for alpha and beta in terms of x? Yeah. I just have alpha equal to x, beta equal to y. So now the question is, can I build any vector in xy? Yes. In fact, any xy can be written as x times the vector 1, 0 plus y times the vector 0, 1. So for example, if you gave me the vector 2, 3, I would know how to build it. I would say, okay, x needs to be 2 in front of the 1, 0 plus 3 in front of the 0, 1. So is this a pretty, are the vectors 1, 0, and 0, 1 very easy to build things with in R2? Yes. This is actually called the standard basis, and it will show up a little bit later. Let's now show that the next vector set also spans R2. So again, we have our x, y, and now we have alpha in front of our first vector, beta in front of our next vector, U2, and gamma in front of negative 1, 3. Okay, so again, we want to set up our system of equations. Okay, so our first equation is x equal to alpha plus beta, that one is kind of small, minus gamma. Y is equal to alpha plus 2 beta plus 3 gamma. And now we want to kind of solve for alpha, beta, gamma. So let's go ahead and put this in a matrix, an augmented matrix. So putting this in an augmented matrix, we would have 1, 1, negative 1 is equal to x, and 1, 2, 3 is equal to y. Now, we want to make this guy a 0. So I can take row 1 minus row 2, okay, and replace my second row. So I'd have 1, 1, negative 1, x, and then I'd have 0, negative 1, negative 1 minus 3 is negative 4, and then x minus y. What do I need to do next? I'd like to make this to be a 1 and then eliminate the first row. So before I do that, I'm just going to add row 1 and row 2 together and replace my row 1. Then I'll multiply row 2 by negative 1. So I'd get 1 plus 0, 1 minus 1, which is 0, negative 5, and I'd get 2x minus y, which I've kind of not left myself enough room. So hold on, let me erase. We'll have it down here. Okay. Okay, so here we would have, okay, what did we have? 1, 0, negative 5, and then we have 2x minus y. And now I'm going to multiply the second row by a negative 1. So I have 0, 1, 4, and y minus x. Okay. Now what do we notice? How many solutions do I have here? Infinitely many. Notice that we have our free variable. Gamma is free again. So if we're wanting to try to write this, we can have alpha is equal to 2x minus y plus 5 gamma. Notice I'm doing 2 steps at once. Beta is equal to y minus x minus 4 gamma, and gamma is free. So what's the easiest thing for me to do for gamma? I can pick anything for gamma. To make it easier, I'm going to pick gamma equal to 0. Okay. So if gamma is equal to 0, what is alpha then? That means alpha, so if gamma is equal to 0, that means alpha is equal to 2x minus y, and beta is equal to y minus x. Okay. So have I been able to solve alpha and beta only in terms of x and y? Yes. So this is a spanning set, but now we're just saying that any xy can be built by taking 2x minus y in front of 1, 1, the 1, 1 vector, plus y minus x in front of the next vector, which is 1, 2, plus 0 times negative 1, 3. Now this would change slightly. If I had picked gamma equal to 1, then this would end up being a 1. Our beta would end up being y minus x minus 4, and alpha would be 2x minus y plus 5. Okay? Alright. Last page. Okay. So notice in each of these examples we found that the span of a set turned out to actually be its own vector space. So now we have a nice way to determine if a set of vectors is a vector space. And so what we can do is we can check to see if we can write a set of vectors as a span. So the goal is to be able to write the set in the form of a span, which is basically the set of all linear combinations, the alpha 1 v1 da, 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 plus alpha n vn. So notice that for each of these we have no restrictions on the constants. That's our goal. We don't want there to be any restrictions at all. So we don't want something like alpha 1 needs to equal alpha 2, or alpha 3 needs to equal 2, or anything like that. Okay, so for example, P1 is equal to the span of x and 1, because we have no restrictions on a and b, and those are the constants in front of x and 1. But let's look at this S example. It's a set of v1 plus a times v2, such that a is in R. Now a has no restriction, But the problem is there is a restriction in front of v1. In other words, it has to have the constant 1 in front of it. So really, when you see the set S, it's really the set of all A times v1 plus B times v2 such that A is equal to 1 and B is real. So is this a vector space? No, because we have this kind of restriction here. So which of the following sets are vector spaces? So for the first one, let's try to write it as a span. Okay, so here we go. Okay, we have A plus 5. Well, or sorry, A times v1 plus 5. Is this a vector space? Well, let's kind of try to understand what this is. If I put a constant in front of each of them, so let's go ahead and have A v1 plus B times 5. Are there restrictions on the constants in front of both of our building blocks, 5 and v1? For A is free. A can be anything. But B needs to equal 1. So is there a restriction? Yes. So the answer is not a vector space. How about the next one? Okay. Now, in here, what's a little bit different is we have A times v1. Sorry, I wrote it as alpha plus alpha times v2 such that alpha is in R. Is there any restriction on the alpha in front of these? No. So this is a vector space, but it's a special vector space where it's only scalar multiples of v1 plus v2. So elements in here are v1 plus v2, 2 v1 plus 2 v2, and things like negative v1 minus v2 are all within here. So in other words, it's all scalar multiples of the sum x1 plus x2. Okay? In other words, this is equal to the span of v1 plus v2. All right. Now sometimes we're given sets and we want to show them they're a vector space by writing it as a span. In our next example, we're going to try to do that. Right now, it's not a span. Okay, not a span yet, because we have a restriction. A0 plus A1 needs to equal 0. So our goal is to try to write it, and try to write this set using only free variables so that we get a set of something such that we only get like things are free. Okay, so that's kind of our goal, if we can do it. So I'm going to look at this restriction and I'm going to say, okay, I have the set of A0 plus A1x such that A0 plus A1 is equal to 0. And I'm going to try to rewrite this. So this is the same thing as saying it's the set of A0 plus A1x such that A0 is equal to negative A1. Do you agree? That's another way to write this. Now our goal is to kind of use this to be able to get rid of any restrictions. So now I'm going to replace my A0 with negative A1. Alright, this is negative A1 plus A1x. Now has that taken care of this restriction? Yeah. Are there any other rules in this set? No, which means A1 is free. There's no restrictions. And so now have I kind of written this as a span? Next, I want to factor out my free variable, so I'd have A1 times what? It'd be negative 1 plus x. So, such that A1 is free. Is this ready to be written as a span? Yeah, we just take our building blocks that are next to our free variables. How many free variables do I have? I have 1. So this is just equal to the span of x minus 1. Okay, so it is a vector space. Yes, hooray! It's a vector space. Okay, so just to summarize a little bit of terminology, we say that V1 through Vn spans a set V if V is the span of this set of vectors. We say a set of vectors is a spanning set for V if V is the span of vectors, or we can say V is spanned by the set of vectors. So you can understand why there can be some confusion with span, because there's a lot of ways to say the same thing. Basically, all of these means that for any arbitrary vector in V, we can find scalars so that we can build them from our set of V1 through Vn. Okay. So these next couple of ones, I want you to pause the video and answer the following questions. Okay, so how would you describe the span of these vectors? So again, sometimes you can represent the span of vectors as a whole space and kind of have some dimension going on here. Okay? So pause it, think about it. Okay, let's talk about 418. So if you think about this, this is the span of 1, 0, 0, 0, 1, 0, and 0, 0, 1. By definition, this is equal to the set of all linear combinations alpha times 1, 0, 0 plus beta times 0, 1, 0 plus gamma times 0, 0, 1, such that alpha, beta, and gamma are free. So my question is, what types of vectors can we build? So first of all, each of these are in R3, so we can immediately get rid of R2. So we know D can't be the right answer because this is 3 space. Now the question is it a point? Is it a line segment? Is it a line, which is 2-dimensional? Or is it R3? So we can ask ourselves, what types of things can we build? And can you build everything in R3 using these building blocks? In other words, if I gave you an arbitrary X, Y, and Z, could you tell what alpha, beta, and gamma need to be to build this? Yes. So in fact, this is just equal to R3. Notice that we have 3 variables. It's 3-dimensional in R3. We're able to hit everything in R3. All right. How about the next one? Now we just have linear combinations of the vector 1, 0, 0. So if we look at that, we're looking at the span. 1, 0, 0 and 0, 1, 0. So we're looking at the span. Put back to blue. Of 1, 0, 0. And again, it doesn't matter that I have it listed sideways or long ways. No. 0, 1, 0. Which is equal to the set of alpha times 1, 0, 0 plus beta times 0, 1, 0, such that alpha and beta are free. So the question is, what is this space? Now, for this, do we have enough vectors to build R3? Can I build any possible vector in here? Could I build an x, y, z? Any x, y, z? Well, no, because we'd have to have z needs to be 0. So it's definitely not R2. It's definitely not R3, R2 and R3, because we can't build anything in the 3rd dimension. And it's also in R3, not in R2. We have 3 spaces. So now the question is, how many dimensions is this? So if you think about this, what's always true about any vector? If you think about this, this is the set of alpha, beta, 0, such that alpha and beta are real. In other words, z is equal to 0 no matter what. If you think about this in 3 space, what does it mean if z is equal to 0? Well, that's just the xy plane. Okay. Right. So it's the xy plane. And so we have to think, okay, well, which one of these is an xy plane? Well, we thought that it wasn't R2 But it turns out, what is the xy plane? The xy plane is R2. So this is R2, because it's definitely not just a line segment, it's definitely not just a point, it's all of this space. And the xy plane is just another way to say R2. So even though this was a space that originally you may think, oh, it's not in R2, like I kind of said before, it's actually can be spanned by kind of this higher dimensional thing. It's like kind of dimensional analysis, kind of compression. We're taking something from 3 space into 2 space. All right, what if we only had one vector now? For the next one, we look at the span of 1, 0, 0, which is equal to alpha times 1, 0, 0, okay, such that alpha is in R. In other words, it's just the set of alpha 0, 0, such that alpha is free. Now, how many dimensions is this? If you think about this, now we have y is equal to 0 and z is equal to 0, which means that, what is this? In the xyz plane, this is just the x-axis. And the x-axis is just, in other words, x can be anything, but y has to be 0 and z has to be 0. So if you're thinking about it in terms of 3 dimensions, if we have our x, y, and z, this says y needs to equal 0, z needs to equal 0, but x can be anything, so it's this line here. So it's actually a full line. And so you can think about this. Here we have three free variables. It kind of makes sense that it's a 3 space. This had 2 free variables, it should be 2-dimensional. This has 1 free variable, it's 1-dimensional. So we have a line. Alright, that's all we have. Now we will start with we'll kind of talk about this next class and do the ice sheet starting in next class. Thanks.